Before we begin solving linear systems of differential equations, I would like to review the concepts of eigenvalues and eigenvectors. We saw that systems of linear differential equations could be expressed using matrices and vectors, and it turns out that the concepts of eigenvalues and eigenvectors from linear algebra are important for understanding how to solve linear systems. So we're going to let A be an n by n matrix, and an eigenvector of A is going to be a non-zero column vector V in Rn such that A times V is equal to lambda times V. And here, A is a matrix, V is a vector, and lambda is a scalar, or just a number. Now, lambda is called the eigenvalue of A. Now, this eigen prefix is actually a German word. It means one's own or its own. And so here we're saying that an eigenvalue is the matrice's own value that's special. An eigenvector is the matrice's own vector that corresponds to that eigenvalue that's special. So sometimes eigen would mean particular value or particular vector, or it would mean special value or special vector. Those are all ways to interpret that German word eigen. Now, my first example is just, I'm going to give you a possible eigenvector, -6, 1, for the matrix -4, 0, 1, and 2. And I want to see, is that an eigenvector? And the way I can figure that out is simply just to multiply A times V. So I'm going to take -4, 0, 1, 2, and I'm going to multiply that by the vector -6, 1. So I'm going to multiply that first row by the column, and I'm going to get 24 plus 0 times 1, so it's just 24. And then for the second row times that column, I'll get a -6 plus 2, that's also -4. And then the question is that a multiple of the vector that we started with? Well, in fact, it is. It's -4 times the vector -6, 1. And so, yes, V is an eigenvector. So V is an eigenvector. And then the eigenvalue is the multiple, which is lambda. So in this case, lambda is equal to -4. So now we see that such vectors do exist and such eigenvalues can exist. The next question, of course, is how can we find eigenvalues and eigenvectors of a matrix? Well, essentially, we want to solve the equation A times V equals lambda times V. But we can rewrite that as A times V minus lambda times V equals 0. Or, furthermore, we can rewrite that as A minus lambda I times V is equal to 0. So here we have a matrix times a vector equals the 0 vector. So essentially, we need to find the null space of A minus lambda I. Now, we know from linear algebra that this has a non-trivial solution if A minus lambda I is not invertible. So if that matrix is invertible, then the only solution is going to be V being the vector 0, 0, if we're using two-dimensional vectors, or V being the 0 vector. And the zero vector cannot be an eigenvector because if we go back to our definition, we said eigenvectors have to be non-zero vectors. So the only way that we can get a non-trivial solution is if the matrix A minus lambda I is not invertible. And one way we can show that it's not invertible is to show that the determinant of A minus lambda I is equal to 0. And so this gives us a two-step method for finding the eigenvalues and the eigenvectors. Okay, step 1 is going to be to solve this equation, solve that the determinant of A minus lambda I is equal to 0. And then you may get one lambda, but you may get multiple values of lambda. So for each lambda, we can solve A minus lambda I times the vector V is equal to 0 to get the eigenvector. So here we obtain the eigenvalues, and then we solve A minus lambda I times V to get the eigenvectors. Okay, so let's have the theorem that we kind of just proved. It says that let A be an n by n matrix. The scalar lambda is an eigenvalue of A if and only if the determinant of A minus lambda I is equal to 0. Now, when we take that determinant of A minus lambda I, it's going to give us an nth degree polynomial. And that polynomial that we said equal to 0 is called the characteristic polynomial of A. And an important fact that we should note is that if V1 and V2 are eigenvectors corresponding to the eigenvalues lambda 1 and lambda 2, and lambda 1 and lambda 2 are not equal to each other, then V1 and V2 must necessarily be linearly independent. And this is the kind of theorem that you're often asked to prove in linear algebra. So I encourage you to look at the definition of linear independence, and then also use the definition of eigenvectors to prove that if you have two eigenvectors that correspond to distinct eigenvalues, then those eigenvectors must be linearly independent.